Hey, welcome back to Calculus. We're going to wrap up section 5.5, looking at some integrals that we do with substitutions, but they're not indefinite integrals, they're definite integrals. They have limits of integration. So I just want to tell you how to treat that so you calculate the right number. And then we'll end the section. The author brings up the idea of symmetry again. If you're integrating a function with some symmetry over a symmetric interval, there's some shortcuts you can take to evaluate the integral. Okay, so just two brief objectives. Let's start off by just kind of looking at the main idea. When you make a substitution, the idea is still the same. We're going to replace the original variable x with some new variable u by letting u equal some function of x and then computing its differential. The thing you have to remember when you're doing a definite integral is you also need to change the limits of integration, right? Because the limits of integration on an integral are values of the variable that is dictating that interval. So if you're integrating something dx, those limits of integration are x values. In this case, we can say that x is between a and b, if a is less than or equal to b. All right, so when you're converting that integral into an integral for u, you can't write x values on the limits of integration. They have to be u values. And how do you switch them? Well, you switch them with the equation that changes x's into u's. So you just simply take your old lower limit of integration a and you evaluate it at your function g to get your u value. You do the same thing for b. Okay, then you take the antiderivative in u, evaluate with the fundamental theorem, and you get your number. You don't have to switch back to the original variable because the answer to a definite integral question is not a function, but it's a number. Okay, so let's just look at some examples. Here I've got an integral from 0 to pi over 2 of cosine x dx. It's a good substitution integral. Maybe you could pause the video and say what you think u should be before I do, but I'm going to let u equal 2x. And when I do the differential, du is then 2 dx, and I have to solve that differential equation for dx. So it's 1/2 du, and then that's all I need to replace my pieces. So I'm going to put the integral cosine of 2x becomes just cosine of u. The dx becomes 1/2 du. And now here's the new part. I need to switch my limits of integration. Okay, so how am I going to do that? I'm going to do that with the equation that changes x's into u's. So I'm going to write, so you don't have to write so much detail, but if x is equal to 0, let me actually move this over so I'm going to have a little bit more room. If x is equal to 0, well, then what is u? U is equal to 2 times 0, or 0. Okay, so that's my new lower limit of integration. It happens to be the same. It can happen. If x is equal to pi over 2, then u is equal to twice that. Well, twice pi over 2 is pi. So my new upper limit of integration is pi. Okay, so pause this for a second and make sure you understand why I did that. These numbers on this new integral, they have to be the values that the new variable varies between. Okay, sometimes they're the same. The lower limit here was 0 in both cases. That's just because 2 times 0 is 0. But in general, you need to use the equation that changes the variable from x to u, or from whatever the original variable is to your new variable, to change the limits of integration. And now we just proceed. This 1/2 I can bring out front. An antiderivative for cosine is sine, right? Because the derivative of sine is cosine, and we need to evaluate that from 0 to pi. So I'm going to take 1/2 the sine of pi minus the sine of 0. Those things are both 0. Sine of pi is 0. The sine of 0 is 0. So we end up getting 0 for this integral. All right, cool. So the integral from 0 to pi over 2 of the cosine of 2x is equal to 0 by our substitution. Nice. Let's try another one. I'm going to do a substitution here. You can pause the video and say what u is before I do. I'm going to let it be 3t minus 1. So taking my derivative, du, it's 3 dt. Solving that for dt, because that's what's left in the integral, that's 1/3 du. Okay, so I'm going to start replacing my pieces. I'm going to kind of write this the way I would the 1/3 being a constant. I'll put it out front right now. So then I just have the integral of u to the 50th du, and the remaining thing to do is to switch my limits. Yeah, I have to take these two x limits, 0 and 1, or t limits, pardon me, they're t limits, and I need to use the equation that changes t's into u's to transform them. Okay, so if t is equal to 0, then u is equal to 3 times 0 minus 1, that's -1. So my new lower limit is -1, and likewise, if t is 1, then u is 3 times 1 minus 1, that's 3 minus 1, that's 2. So it's the integral in u from -1 to 2. That's the appropriate limits of integration. And now you can forget all about t and just do the antiderivative. So I'm going to take my 1/3 as a constant. I'm going to use the power rule. So I'm adding 1 to that exponent and dividing by the new exponent. And then I just have to evaluate that thing. 3 times 51 is 153, so I'll leave it like that as a constant out front. And then I have to take the 51st power of 2. I don't have my calculator here with me, so I'm just going to write 2 to the 51. And then I have to subtract the negative 51st power of -1. Okay, so that's a -1 to the 51. And -1 to the 51, because 51 is odd, is -1. So we can simplify this just a teeny bit to make it look a little bit nicer. It's 1 over 153 times 2 to the 51, a very large number. And then subtracting -1, I might as well write +1. Okay, so there's your second integral. Let's do another one. This time, looking at the integral from 0 to 1 of that expression, x minus 1 times e to the x minus 1 squared. If you've taken my previous advice with an exponential, you can always try to let u be what's in the exponent. So I'm going to let it be x minus 1 quantity squared, and then I have to differentiate that with the chain rule. That's 2 times the quantity x minus 1 times 1 dx. All right. And I can see that I should solve that for x minus 1 dx up in the integral. So I've got 1/2 du is equal to that. So that's going to let me substitute out all my expressions in the integrand. So I have the integral e to the u du, but I have to put a factor of 1/2 out front, all right, from my differential equation. And now I just have to transform my limits. So when the original variable x is 0, well, u is equal to 0 minus 1 quantity squared, that's 1. Okay, and when x is equal to 1, u is equal to 1 minus 1 quantity squared, that's 0. So the new limits of integration for the u integral are 0 to 1, and I can evaluate it like that. If you prefer to have your upper limit of integration always greater than or equal to your lower limit of integration, we could use an integral property. This is a good chance for me to bring it up. I can reverse those limits of integration as long as I'm willing to pay with that minus sign. All right, and now just continuing, sorry these aren't the best notes in the world, but minus 1/2 times the antiderivative of e to the u, that's itself, from 0 to 1. I like to leave the constant factor out front, so I'm going to take e to the 1 minus e to the 0. And I think I'll leave my answer like that, or if you prefer, probably in the back of the book, just to make things look prettier, they probably write something like 1/2 times 1 minus e. Okay, so there's that third integral. Good. All right, so that's, I think, a sufficient number of examples to illustrate the idea. Just to say it one more time, when you're doing a definite integral by substitution, don't forget to change your limits of integration. You change your limits of integration with the same equation that changes variables. Okay, you don't have to switch back to the original variable because you're not trying to come up with some function. A definite integral is a number. Okay, and you can evaluate that number in the new limits of integration. Okay, so we'll keep this short. Let's just talk real briefly about what the author is mentioning here about symmetry. We've already talked about what I mean by even and odd functions, so I won't go into that here, other than just to remind you that even functions have symmetry across the y-axis. So how the function looks for positive x is the same as negative x. Odd functions have rotational symmetry about the origin. So f of negative x is negative f of x. So these are kind of quintessential pictures of what even and odd symmetry look like. And the result here is actually pretty straightforward. It's just saying that if you're going to integrate something, an even function, over a symmetric interval, minus a to a, well, you could always just take 2 times the integral from 0 to a. Yeah? So it's just saying that the total shaded area over here is twice the right-hand side. Why is that convenient? Because 0 is usually a little bit easier to plug into functions than arbitrary numbers. So it just makes the arithmetic simpler. If your function's odd, well, then that symmetry, because it's rotational, is going to make half the area above the axis and half the area below the axis, and they'll be equal in area. So the integral of an odd function over a symmetric interval will always give 0. These two quantities are the same area, and they have opposite signs as signed area. So you're going to get a 0. Okay, so it's just sort of a convenient. If you happen to notice your function is odd, again, the interval is minus a to a. It has to be a symmetric interval. Then you know the integral will be 0. You don't have to do any calculation. Okay, let's just try it out. Here I've got a nice symmetric interval, minus 2 to 2. That's usually the clue of when I think about this. If you give me an integral and I see that the lower limit and upper limit of integration are opposite of each other, then I ask myself, oh, is this an even or an odd function? And x to the 6th plus 1 is an even function. If you plug in minus x, you'll get the same thing as plugging in x. So this just means that I could double the integral from 0 to 2 of the same expression and get the same answer. Okay, and that lower limit of 0 will be convenient here when we do the arithmetic. Let me show you. If I find an antiderivative here, it's 1/7 x to the 7th plus x. Right? So I don't want to have to plug in -2 and do all of that arithmetic. I can just take the upper limit. So I get 2 to the 7th over 7 plus 2 minus the lower limit will give me 0 because there's an x in both terms. So that made the computation sort of easier arithmetic-wise. If I multiply that 2 through there, I can write this as 2 to the 8th over 7 plus 4. Right? So the symmetry eased the arithmetic. Maybe you can take a second and evaluate the integral without using that symmetry trick, and you'll see, you'll get the same answer, but you'll have to do some minus signs and combine some like terms. Okay, last example. Again, you hand me an integral with lower and upper limits of integration that are opposites of each other. Then I wonder, is it an even or an odd function? Okay, I can see that the denominator of this expression is even. When you plug in -x, you'll get the same thing as x, but the tangent function, maybe you remember from trigonometry, is odd. The tangent of the negative of opposite of x is the opposite of tangent of x. So because this function is an odd function divided by an even function, the whole thing is odd, so I don't have to do any computation. This thing is 0 because the tangent of -x is the negative of tangent x. It's an odd function in the numerator, an even function in the denominator, so it's an odd function total. Okay, so I know this was short. I hope that these examples were illustrative, and I hope you're practicing lots of integrals by substitution.